You've flipped a light switch 10,000 times in your life. Click. Light appears. Instant, effortless, reliable. But have you ever asked what happens in the milliseconds between the click and the light? Have you ever wondered where that electricity was 1 second before you needed it? Most people haven't. They just assume it's stored somewhere, waiting, ready to flow, but it's not. When you flip that switch, you're not releasing stored electricity. You're sending a signal that ripples through the entire grid, and somewhere, sometimes hundreds of miles away, a turbine spins slightly harder at that exact moment to generate the power you just demanded. There is no storage. There is no buffer. The grid has about 4 seconds before total collapse. Tesla knew this. He built the system anyway. And once you understand why AC electricity cannot be stored, you'll see why our entire civilization is more fragile than you think. Let me show you what I mean. The standard explanation you might get is AC electricity is alternating current. It changes direction 60 times per second, so it can't sit still in a battery. That's not wrong exactly, but it's missing the point. Because once you see what's really happening, once you understand what AC electricity actually is, you realize the problem isn't just technical, it's fundamental. There's something here that nobody talks about, something that connects to why your city can have blackouts, why solar panels create grid instability, why California has a duck curve problem, why battery technology is suddenly worth hundreds of billions of dollars. Tesla saw this coming. He knew exactly what trade-off he was making when he beat Edison's DC system. Transmission efficiency for storage, distance for stability. Let me show you what I mean. Start with something simple, something you can test right now. Start with something simple, a battery. Pick up your phone. Right now, feel the weight of it. Most of that weight, maybe 40% of the entire device, is battery. Lithium-ion cells storing electrical energy as chemical potential. You've charged this battery hundreds of times. You plug it in, electrons flow in, chemical bonds rearrange, energy gets stored. Unplug it, use your phone all day. Those chemical bonds break, electrons flow out, stored energy, released on demand. That's DC electricity, direct current, electrons flowing in one direction like water through a pipe. And yes, you can absolutely store it. That's what every battery does. Now plug your phone into the wall. Stop and think about that for a second. What's coming out of that wall socket? A C electricity, alternating current, not a steady flow in one direction. A wave, electrons sloshing back and forth, changing direction 60 times every second. In the US, it's exactly 60 hertz, 60 complete cycles per second. In Europe, 55 hertz. Here's what's actually happening. The voltage at your wall socket isn't constant. It's a sine wave, oscillating from plus 120 volts to minus 120 volts, and back again, 60 times per second. The electrons aren't traveling from the power plant to your house. They're vibrating in place, but that's just the surface. Because if that's true, it raises another question. How do you store a vibration? You can't store AC electricity in a battery because a battery is fundamentally directional. Think of it like this. A battery is a chemical reaction that wants to run one way. Lithium ions move from one electrode to another, releasing electrons that flow out. Charging reverses this. You force the ions back, storing energy. But that only works with a consistent direction. Push electrons in, pull electrons out. A C doesn't have a consistent direction. It's alternating, back and forth, 60 times per second. If you tried to connect a battery directly to AC power, the current would try to charge it, then immediately discharge it, then charge it again, then discharge it again, 60 times per second. The battery wouldn't store anything. It would just heat up and probably explode. Think about what that means. Every device in your home that runs on batteries, your phone, your laptop, your electric toothbrush, has a converter inside it. That little brick on your charging cable, that's converting AC from the wall into DC for the battery. It's not just reducing voltage, it's fundamentally changing the nature of the current. Tesla knew this in 1891 when he demonstrated his AC system. He knew you couldn't store it, he chose it anyway. But wait, that raises another question. If AC can't be stored, and everything in your house needs electricity right now when you flip the switch, then where does that electricity come from? Here's where it gets strange. When you turn on a light in your house, that electricity is being generated at that exact moment by a power plant somewhere on the grid. Not stored and released. Generated. Right then. The grid doesn't store electricity. It balances it. Every single Second, the grid operators are matching generation to consumption across the entire network. Power plants are spinning turbines, massive coils of wire rotating through magnetic fields, and those turbines generate AC electricity by physically rotating. When you flip your light switch, you add load to the grid. That load creates resistance, and that resistance makes every turbine on the grid work slightly harder. Here's the thing that most people miss. Those turbines are all synchronized. They're all spinning at exactly the same frequency, 60 hertz in North America. They have to be. If they drift out of sync, the grid becomes unstable. Equipment fails, blackouts cascade. This synchronization is not automatic. It's maintained constantly in real time by adding or removing generation to match demand. Think about what this means. Right now, as you're reading this, if you turn on your air conditioner, a power plant somewhere responds. A valve opens slightly more. More steam hits the turbine. The turbine maintains its 60 Hz frequency despite your added load. The grid has some inertia. The massive spinning turbines provide a buffer measured in seconds. Not hours, not minutes, seconds. We've tested this. We know exactly how long the grid can survive without active balancing, about 4 seconds. But that's still not the full story. If the grid is this delicate, if there's essentially no storage, then why did Tesla fight so hard for AC instead of Edison's DC system? Now we're getting to the core. Tesla chose AC not because it was better for storage. He chose it because it was better for transmission. Here's the fundamental physics. When you send electricity through a wire over long distances, you lose energy to resistance. The wire heats up. Power is wasted. This loss is proportional to the current squared. Double the current. You get 4 times the heat loss. But here's the beautiful part. Power, the actual useful energy, is voltage times current. So if you can transmit at high voltage and low current, you lose less energy. DC can't easily change voltage. Edison's system transmitted at the same voltage it was used at. That meant massive current for any real power, which meant massive losses over distance. Edison's power plants had to be within a mile of the customers. A C can change voltage trivially. That's what a transformer does. No moving parts, just coils of wire. Step the voltage up to 500,000 volts for transmission, you drop the current by the same factor, and suddenly you can send power hundreds of miles with acceptable losses. This should break your brain a little. Tesla sacrificed storage, the ability to save electricity for when you need it, to gain distance, the ability to generate it far away and transmit it efficiently. He built a system where every joule of electricity consumed must be generated at that exact moment, but that electricity can come from hundreds of miles away. And here's what that means for civilization. Here's what nobody tells you. The entire modern world runs on a high-wire act with no safety net. In your normal experience of the world, the lights just work. You flip the switch, light appears. Reliable, stable. You assume there's some buffer, some reserve capacity, some warehouse of electricity ready to fill any gap, except that's completely false. Pause. The electrical grid has essentially zero storage. Right now, this second, power plants across the continent are generating exactly, and I mean exactly, the amount of electricity being consumed. Not approximately. Exactly. Let me prove it to you. The grid frequency is 60.00 hertz in North America, not 60.1, not 59.9, exactly 60.00, maintained to within 0.02 hertz. Every clock that runs on AC power, those old digital clocks, alarm clocks, microwave displays, they count cycles to measure time. If the grid drifted to 59 hertz for 1 hour, those clocks would lose 60 seconds. We've measured how long the grid can survive a sudden imbalance. In 2003, a software bug in Ohio caused operators to lose visibility into grid status. Trees touched a sagging power line. That line failed. Load redistributed. Other lines overloaded. 9 seconds later, 50 million people lost power. 9 seconds from first failure to cascading blackout. Think about what this means. Every time you charge your car, a turbine spins harder. Every time a factory starts up, generation increases to match. Every time the sun sets and a million solar panels stop producing, something else has to ramp up to fill that exact gap. There is no warehouse of electricity. The grid has about 4 seconds of rotational inertia in spinning turbines before frequency collapse begins. That's it. Right now, power plants are generating exactly what you're using, not what you might use, not what you used yesterday, what you're using right now. This isn't speculation. This isn't approximation. This is the actual structure of the grid. This is measured reality. And once you see this, you realize AC electricity isn't just hard to store, it's created a civilization that runs on perfect real-time balance with almost no margin for error. Now here's what people miss when they learn just about AC versus DC. This isn't just about electricity. This fundamental constraint, the impossibility of storing AC, connects to everything about how modern civilization actually functions. The same real-time balancing act that keeps your lights on also creates the duck curve, when solar panels flood the grid with power during the day, then vanish at sunset, requiring massive generation ramps that stress the entire system, makes renewable integration so challenging. Wind and solar generate when nature decides, not when we need it, and without storage, the grid must have backup generation spinning and ready every moment. Causes rolling blackouts, California, Texas, South Africa. When demand spikes or generation fails, there's no reserve to draw from, so they cut power to neighborhoods in rotation, drives the battery revolution, Tesla's Powerwall, grid-scale lithium facilities, experimental gravity storage, all attempts to add the buffer that Tesla's AC system fundamentally lacks. Explains why baseload power still matters. Nuclear and coal plants can't quickly ramp up and down, but they provide the stable generation that keeps frequency locked at 60 Hertz. What looks like separate problems, renewable integration, blackout prevention, battery development, grid stability, is actually one problem manifesting in different ways. The absence of storage in an AC system. You're not separate from this. Right now, your existence is coupled in real time to a power plant somewhere. The electrons in your light bulb are vibrating in perfect synchrony with a turbine miles away. You're part of a continental machine with no pause button. That's not fragile. That's magnificent. That's what Tesla built. A system so efficient at transmission it could unify a continent, but so dependent on perfect balance it could collapse in seconds. So, when you flip that light switch next time, remember what you're actually doing. So why can't you store AC electricity? Because AC isn't a thing you can hold. It's a synchronized vibration across an entire grid. It's a wave that only exists in motion. Storage requires direction, stability, stasis. A C is none of those things. You can convert it to DC and store that. You can store energy in other forms, pump water uphill, compress air, spin flywheels. But you cannot store the alternating current itself. The wave must keep moving, or it ceases to be. But understanding this isn't just about electricity. It's about the trade-offs that shape civilization. Tesla saw the choice clearly in 1893. He could build a system optimized for storage, Edison's DC, limited to a mile radius, requiring a power plant in every neighborhood. Or he could build a system optimized for transmission, AC, capable of carrying power hundreds of miles, but requiring perfect real-time balance. He chose transmission. He chose distance over storage. He chose to unify the grid at the cost of making it fragile. And he was right. Because of that choice, we have refrigeration, air conditioning, electric trains, aluminum production, the internet, modern cities. We have civilization at scale. We also have rolling blackouts and grid instability and a desperate race to add storage capacity before renewable integration breaks the system Tesla built. That's what AC electricity really is. Not stored power waiting to flow. A high-wire act performed continuously across a continent, synchronized to the millisecond, with no safety net. Not comfort, not simplicity, truth. If this journey into the real-time nature of electricity changed how you see that light switch on your wall, subscribe and share it with someone who still thinks power is stored somewhere waiting for them. What other everyday technologies do you think hide this kind of fragile complexity? Tell me in the comments.